All right, you guys, here is the, oops, wrong stuff. All right, so let me show you guys, let me go to modules and show you guys the last lab I put in there for you. There's just going to be one more lab, and there's too many labs already. You guys done enough work. Just one more lab. So here is the Milky Way lab. When you finish this, there's going to be just one more lab. So I put in the Word, and I also put a PDF file there for you. I also put the lecture here for you guys. So if you want to see the lecture before you do the lab, you can. And let me just download this just to show you guys. No, I don't think you guys can see this once I open it, or can you? Can you guys see this? It says Milky Way Galaxy.
Yeah, we can.
Oh, you can. Okay, good. So this is the Milky Way Galaxy lab. I just have a couple of pictures in here of side view and face view. And there's just a whole bunch of questions. All you guys need to do is to circle the 1, 2, 3 here. So it'll be really easy to do. It's a super easy lab. You guys should all ace it. And there's a couple of things that I need to tell you. One question has to do with globular clusters being metal poor or metal rich. Okay. And another one has to do, why is the sun metal rich? So obviously the sun is metal rich and the stars in globular clusters are metal poor. I'll talk about that in just a couple of seconds. And then question number 4 has you actually do the Hubble diagram. Now I did the Hubble diagram in the class, and I can do it again on the board for you today so you guys know what this Hubble lab is all about. This Hubble classification of galaxies. And then at the end, there's a question about 21 centimeter radio waves, and I'm going to go over that as well. Is there anything else that you guys want me to go over? Now here, it's question 17. It's a difficult question because there's about 78 galaxies, but if you guys Google it, it's going to say 54 galaxies. So I'm basically giving you guys the answer to question 17. There's 78 galaxies, 3 of which are actual spiral galaxies, and the rest of them are irregular galaxies or dwarf elliptical galaxies. So they're like little tiny miniature galaxies. So only 3 big galaxies in the local group of galaxies around us within 10 million light years, basically. Okay. That's it. That's what I was going to say. So I was going to do the classification of galaxies and also do the 21 centimeter, explain the 21 centimeter radio waves. And then I was going to show you guys the image uploads and image downloads and stuff from NASA. Has anybody gotten any images back yet?
I have.
You have?
I came through today.
No.
Yeah.
Okay, what did you get back? Because I've only got one black and white. I couldn't get any colors.
A few of them.
Yet.
A few of them for me were black and white. So I did it on the 10th. So I did it again on the 11th. On the 11th, they came out a lot more better. So I got like 3 good images.
So there are 3 more images. You mean RGB, red, green, and blue?
I did one that was red, green, and blue, and that one came out good, but it's sort of white, not really color. So
No. Did you get the red, green, and blue images? The 3 images are red.
Yeah.
Green, and blue. Okay. Yeah, they all look white at the beginning. We have to play with it before we change the thing. Okay, so you got 3 images. Congratulations, because I'm only getting my images from Southern Sky. I'm getting stuff I've never even seen before, you know, which is pretty impressive. But I'm not getting my color images, and I asked for it yesterday. I asked for it a week ago. So I keep asking, but I'm not getting it. But at least you guys are getting it. So maybe it's cloudy in Arizona. I'm not sure. Anybody else besides Bethany? I mean, besides Talia. I'm sorry.
I haven't even gotten a message back or anything about my images.
Message back. Did you ask for it? Did you ask for images?
I asked for like my images, and they haven't like responded back.
Right. If it's cloudy, they're not going to send you anything. If it's clear, they're going to send it to you, just like Talia's did.
Yeah.
So this week this is it, because the moon is already going to get big again.
Mhm.
So we got to do it now. Remember the 14th? I remember Bethany said that like a week ago, or 2 weeks ago. She said the 14th is the dark of the moon. Remember that? Yeah. So this is it. This is our last chance to get the images. And if you can't get anything from Arizona, you can always ask for the southern sky. Because I got my images from southern sky back real fast. So let's do it by Wednesday. Let's see if you guys can get all your images back by Wednesday, okay? Please. Pretty please. All right,
Do
so
you have any tips on how to get them to show up color?
yes.
None of mine did, even though I followed all the instructions and selected color.
Oh, okay. All right. So you
They
got
all
images.
came out black and white. So any
Okay, so they're
recommendations for-
supposed to be black and white.
Oh, okay. I thought you wanted like a color filter on some of them.
Yeah. No, you wanted R, G, and B.
Yeah, that's what I
So
did.
you get red, green, and blue images, which are black and white.
Oh, okay. Just making sure.
And then you
For some
use
reason I thought I was going to be able to see the color.
No. You see the color once you put the RGB images together in their processor.
Okay.
You have to put it in their processor.
Cool.
Which I'll show you guys in just a few minutes. Let me go over these two questions that we had before on the classification of galaxies, the Hubble classification of galaxies, and then the 21 centimeter waves. Maybe I'll do the 21 centimeter first. Okay, so allow me, if there's any other questions, let me get on the board and do that for you guys. Now, I don't know if you guys remember, but I remember previously I told you guys this is almost like the proof that God exists or something, right? Yeah, I'm pretty impressed with the universe. I don't know if you guys have noticed, but I'm just pretty impressed the way the whole thing is put together. It's like, what? Every time I see something, I go, what? It's a good thing I'm not a religious person, or I'd be like one of those, like something like deep into religion or something, but I'm not religious. But I am into God, even though I'm not into religious, right? By God, I mean, what do I mean exactly? I mean, the universe. It's like the whole thing is a miracle. You guys just existing right there is a miracle, right? The chances of you guys existing at all, like Daniela existing, right? The chances of her existing is something like 1 in a billion, that she even exists. And yet we're here, right? So obviously life is doable because we're the proof that life does exist, right? And yet you put all these chemicals together and it starts walking and becoming Daniela. It's like, what? How does that happen, right? It's pretty amazing. Well, anyway, so we're all made of this stuff called atoms, right? And atoms are made of things that we simplify, like a nucleus, like a proton. And you have, sometimes you do, sometimes you don't have neutrons in the atom. And then you have electrons that orbit the proton, right? Well, not exactly that simple, actually, right? There's an electron field. So there's a field, like a magnetic field, there's an electron field. They may not actually be an electron. An electron may not even exist. So,
Hey, Sina, are you trying to share with us? Because all I see is the whiteboard.
No, I'm not trying to share anything with you.
Okay.
I'm just showing you a whiteboard right now.
Just making sure.
So basically what I'm trying to tell you is that the atomic structure that we've been talking about is kind of like a really, really simplified version of something that is super, complicated. And so that's what I'm trying to explain to you guys, right? So in other words, there could just be like a wave, like one wave in the entire universe, right? Just one wave.
I think I sent.
And within one wave, you have like sub waves or something. And we're talking about a lot of little tiny waves. So we can say there's this giant wave, and you and I are made of things that are just disturbances in this wave. Does that make sense to you guys at all?
Yeah.
Well, let's see. Let's go back to simplification anyways. So, in the galaxy, you have this nucleus and you have the spiral arms, right, coming out. And this is where the stars are made, in these spiral arms of the galaxy. There's two kinds of hydrogen gas here. One kind of hydrogen gas is luminous, like reddish, basically, like that, right? They're all over the place here. And we used to be one of them. There used to be a hydrogen gas cloud, a big hydrogen gas cloud. The sun and his brothers and sisters, they all came from this hydrogen gas cloud, maybe 1,000 brothers and sisters. Now we've lost the brothers and sisters. We don't know where we came from. But this is where the stars are made, in these red hydrogen clouds. We call these the H2 regions. These H2 regions are just glowing because there's stars within them. There's lots and lots of stars within these hydrogen gas clouds. They were just born, right? Like born yesterday. Every day there's like new stars being born in the galaxy someplace in these hydrogen clouds of gas we call the H2 regions. Let me do this so that you guys don't do that. All right. Now there's some other place here. These other places, this is neutral hydrogen cloud. So these H2 regions, we say they're ionized hydrogen gas. Ionized hydrogen gas. All right, this H2 regions. We call them ionized hydrogen gas. So this is hydrogen, right? This is like a proton and an electron orbiting it, basically, right? That's hydrogen. But that's neutral hydrogen gas because you have a proton and an electron. The proton and electron have a charge. One of them has a positive charge, the other one has a negative charge. The negative charge and the positive charge are exactly the same amount. So they cancel each other out. So we say this is neutral hydrogen. Neutral hydrogen, all right? Neutral hydrogen. Because there's no net charge, right? So if you had 2 electrons, it would be negatively charged. If you had 2 protons and 1 electron, it would be positively charged. Right now, this would be neutral. Well, in these hydrogen gas clouds, these are ions, meaning that they look like this. Just 1 proton. That's it. Ion, right? And then they capture an electron. When they capture an electron, say a free electron is coming from some star or something. Comes in and then it gets captured. When it gets captured, then this red light comes out, this red photon. And that's why this thing is reddish, right? These clouds of gas are reddish because they're glowing by this method that I just told you. There's a whole bunch of electrons. These electrons can come in and join. Or there's an electron there, and that electron pops and leaves, and then another one comes in. Regardless, this is how this thing is made, right? This reddish clouds. So they're ionized hydrogen clouds. Now, and these green things here, these green gas clouds, which are pretty vast. They're huge. Then they also exist in the spiral arms of the galaxy. This is like places where there's hydrogen, and there's no action yet, you know, it's like there's no star building going on yet. In the H2 regions, this is a star forming region, right? A star forming. That's where stuff is going on. Here, no, there's no star forming. This is called neutral hydrogen gas clouds. All right, that's a neutral hydrogen gas clouds. So there, you have to sit there for a long time. Eventually, gravity will take over, you know, make the gas cloud condense, maybe a star or 2 start forming, and then they glow, and after they glow, they make it into one of these red hydrogen gas clouds. But so far, they haven't, so they just kind of sit there. So these neutral hydrogen clouds, they look like this. So in these neutral hydrogen gas clouds in the galaxy, you have a proton and an electron here, right, like that. And they sit there and they sit there maybe for, maybe 5 million years. And after 5 million years, the electron changes its direction of spin. Now, the spin that I'm talking about is a quantum state. So they change their quantum state all of a sudden, as though they have, should I say it? As though they have consciousness, like they know what the heck is going on. How do they know anything is going on? Like I was telling you, these electrons are like size 0. They're just a disturbance in space. But they change their state all of a sudden. So in this case, I'm going to explain it in terms that are really easy to grasp so you guys can have a better, understanding of it for your lab. And so let's say this electron doesn't just orbit around a proton. It also spins, like the Earth spins as it goes around the sun, right? This is a revolution, but it also spins. So the electrons do the same thing. They also have a spin like that. So they spin at the same time that they're orbiting a proton, right? But then after a few million years of doing nothing at all of a sudden they change the direction of spin. So all of a sudden the electron, instead of spinning, let's say counterclockwise, it spins the other way. It changes the direction of spin. So this is a change and the direction of spin. And then what happens is that when they change the direction of spin, they emit a photon, they emit light. But this light is not a visible light to the human eye. This is a radio wave. It's still a photon. Radio waves travel at the speed of light. There are light. It's just that we cannot see them with our eyes, human being eyes. And so what happens is that once they change the direction of spin, they send out this energy, and then this is a radio wave. And this radio wave has a wavelength, the distance between the peak to peak of a wave. Just like in ocean waves, you have a wave and another wave. The distance between the peak of one wave to the peak of the next wave is from here to here is about 21 centimeters. 21 centimeters is about this big, about 8 inches. So it's about an 8-inch wave. And you can pick it up. You can pick this up with a radio telescope. You can pick it up with an antenna. It was first discovered like a TV antenna. You can pick it up with a TV antenna. So when they looked at the galaxy with the 21 centimeter radio detector, what they found was that the entire galaxy, all the spiral arms, can be detected by using a radio telescope tuned into this 21 centimeter waves. Because there's like gazillions of electrons. So at any given time, even though it may take millions of years for this to happen, at any given time, there's quite a few of these happening. And so the whole spiral arms of the galaxy are emitting this 21 centimeter radio wave. It's as though if you wanted to talk to somebody in the universe, it may be good to use this 21 centimeter radio wave. It's like the natural frequency of the galaxy. The galaxy is tuning this to this radio wave. The whole galaxy is emitting this 21 centimeter radio wave. And so when we look, we can't see around the sun. We can only see about 10,000 light years. So if, let's say, you're here, you can only see about this much. So how do we even know these spiral arms exist? Because we can't see farther. There's so much dust and gas around us. Well, radio waves go right through the dust and gas, right? Just like radio waves go around through, around your house, right? Radio waves, there's such a huge waves that they go right around trees and any kind of obstacle. So that's how we observe the whole galaxy, using radio waves. Sometimes we use infrared as well, but it's not as good as radio waves. Radio waves go right through everything, dust, gas, everything. And so that's what this 21 centimeter wave is about. Is there any questions before I erase it? that make sense to you guys? Okay, good.
Yep.
In a
And
way,
so
it does. Yeah.
you wanted to draw in the lab?
You can, if you like. You
Okay.
can draw all this stuff here and show me, where the heck this radio wave comes from. This 21
Okay.
cent radio
For
wave.
the Hubble, for the Hubble?
For the Hubble? No, not for the Hubble. Let
Okay.
me show you the question that I'm talking about. Just don't do anything in the lab yet. Just write down these notes. Okay, let's see.
Oh, hey, Professor.
Can you guys see this? Yeah, go ahead. I'm listening to you.
No, I was just gonna say, I was just checking my email for a second while writing what you had on the board down, and I just found out that I got sent the images like
Oh, okay.
1 day.
All right, all right. Good, good.
I'm good.
Yeah, we'll process the images together on Wednesday. So do you see the question number 20? Where and how do the 21 center radio waves originate in our galaxy? Where and how? I just showed you guys where and how. Okay?
It's from the spirals.
Yeah, that's where and how. Now we're going to get into this. Don't draw it yet. Let me finish drawing it. You just take notes and then put it in your lab when you're done. All right? So this is question number 12. I'm going to go over the Hubble diagram of galaxies. What kind of galaxies exist in the universe, right? So let's see. So Hubble looked at, thousands of galaxies. And what he noticed is that galaxies appear to be outside of the Milky Way. Because at the turn of the century, 20th century, they used to think that galaxies are just places inside our galaxy. Well, it turns out they're outside of our galaxy. They're much, much farther than we thought. And so 120 years ago, they used to think that the universe is the Milky Way galaxy. The whole universe is the Milky Way galaxy. Then they found out the Milky Way galaxy is just one little tiny speck in this ocean of space that is, maybe about 100 billion light years in diameter, right? It's a huge place. And ours is just a tiny little galaxy. So when he looked at a lot of galaxies, what he found was that these galaxies have shapes that repeat, like from one location to another, same galaxy-looking types. So he classified these galaxies according to shape. It's called morphological. Morphological means according to shape. Morphing, you guys seen morphing? It means shape. I don't know if you guys ever seen morphing. Like there's programs that change the shape of your face, It's called morphing, like Star Wars. All right, so we say this is the Hubble tuning fork diagram. Oh, geez, I don't know if tuning is two ends or one end, you guys. I think it's just one end. Anyways, tuning fork diagram. This is classification of galaxies. All right, so this is all the galaxies that we see in the universe. When we look out, this is what we see. Now, they're all made of the same stuff as our galaxy. There's dust and gas, there's stars, there is, all kinds of stuff like globular clusters, there is, and then everything that we have in our galaxy. Besides OB of fine girl stars, there's like clouds of gas, there is red supergiants, red giants, open clusters, there is planetary nebula, there's supernovas that goes off, all kinds of stuff, but they're about the same. But their shape, right, morphological shape, that's different. So a tuning fork looks like this. I don't know if you guys have ever tuned you guys ever tuned a musical instrument? It looks like that, right? That's a tuning fork. You go ding, it vibrates, right? So it's like a tuning fork. And the tuning fork is this way, actually. It goes like that. So it starts with elliptical galaxies. So here are the elliptical galaxies. elliptical galaxies. So elliptical galaxies have some that are perfectly spherical, and they're pretty big actually. They're like a big gigantic ball of stars, and they have no dust or gas. In other words, the star formation is over with. They don't make any new stars. The stars are all like red giants and red supergiants. They're old, ancient stars. And if there is any like little tiny M stars that take forever to evolve, we don't see them because they're so faint. But what we do see, lots of red giants and red supergiants. So there's a lot of stars with no gas and no dust. So these guys have no gas or dust. Or dust. And we say they have different populations. So galaxies have stars that are population 1 or population 2. Population 1, you can write down very young stars. Population 2, very old stars or evolved stars like red giants and red supergiants are population 2. The sun is population 1. All right, so stars that are like on the H&R diagram, they're the main sequence stars, they're population 1. Stars that have evolved, they're population 2. So there's only population 2 here. Only pop 2 stars. Okay, so that's what's special about these galaxies. It seems like what these guys are, they resemble the bulge of our galaxy. So it seems like when galaxies collide, this is the result of the collision, really. So elliptical galaxies, we call them E, big E. And depending on how cigar-shaped they are, like watermelon-shaped they are, it changes to up to 7, from 0 to 7. So 0 means perfectly spherical, E0. So E1 will be a little more like a watermelon. E2, E3, E4, E5. So E3 will look something like this. This will be like E3. Then E7 will look more like this. This is the most cigar shape they get. So E0, E1, E2, E3, E4, E5, E6, E7. E7 is the most elliptical they get. Now, what's in them is a whole bunch of stars. And I'm not going to draw every little star. There's like billions of dots here, right? So there's stars everywhere here. You can see right through them because there's no dust and gas. Remember, only population 2. The dust and gas has already been used up. There's no dust and gas left. Star formation is finished. And then there is some galaxies that are just like these, but they're miniature, little tiny ones. So we call them the dwarf ellipticals. And they're the same exact thing, except they're tiny versions. These are the dwarf ellipticals. So they look like this. Maybe this is an E4, E7. And then we say D at the beginning separates them from the regular ellipticals. They're pretty big. So these guys are DE0, dwarf elliptical galaxies. Dwarf E4, DE4, DE7. That's how we classify the elliptical galaxies. So you can have DE0, DE5, DE6, like that. So these are the elliptical galaxies. Any questions about the ellipticals? Okay. Now, there are some galaxies that have a lot of dust and gas, and these are the spiral galaxies. They have a lot of dust and gas. But there's kind of like in between the two galaxies, ellipticals and spirals, there's one kind called lenticulars. And these lenticulars are exactly like our galaxy, except they don't have spiral arms. No spiral arms. That's kind of weird. So they, from the edge, they look kind of like this. Kind of like that from the edge. And so we say these are called lenticulars. Lenticulars. Some of these lenticulars also have, so we call them spirals of zero kind. So these are S0s, not spiral yet. And some of them have spiral, no spiral arms, but they have bars in them in the center. So this is called S, the big B, and then 0, where B means barred. A bar is just like the bar in the Milky Way galaxy is made out of dust and gas. It's just a big bar of dust and gas and stars like that. That's called a bar. So these are the barred ones. Now you can see this is this section of the tuning fork. Now we're going to get into the actual tuning fork opening up here. So then we're going to have the spirals. And spirals begin with their nucleus, that are gigantically big, medium size, and small. So the size of the bulge, very big, medium size, and then smaller. And then we have some that have same kind of nucleus, but they have a bar of dust and gas again. Like this bar of dust and gas here. They have a bar of dust and gas going right through the nucleus of the galaxy. So we say these are the barred spirals. These are like the regular spirals and then barred spirals. And these guys have spiral arms that come directly from the nucleus. Like that. We call these S for spiral, and then little a, SA type galaxies. So SA galaxies have a large nucleus and very tightly wound up spiral arms. So the arms are very tightly wound up like this, really tight spiral arms. So as they open up, their nucleus gets smaller. Like these guys here, just opened up. Like that. And really open like that. So medium-sized nucleus, and then the spiral arms are kind of open. These are called big S, little b. And these are called big S, little c. And then with the bars, the spiral arms come from the end of the bars. Like that. A little more open, and then really open. Like that. So these are called S, big B for barred, and then little a. S, big B, little b. S, big B, little c. SBA, SBB, SBC, SA, SB, SC. So that depends on whether or not they have a bar and also whether or not they have a large bulge and very tightly wound up spiral arms or kind of loose spiral arms. So like if I'm a galaxy, it'll be really tight like that, or a little looser like that. So it depends on how tight the spiral arms are and how large the bulge of the galaxy is, the central bulge of the galaxy is. All right, so what do they all have in common? They have population 1 and population 2. And lenticulars are exactly the same, except lenticulars don't have spiral arms. They're just weird, exactly like the Milky Way, but they don't have any spiral arms. So here they have no spiral arms, but they have all else as spirals. So what do spirals have? Spirals have population 1 and population 2. So remember again, I'll remind you one more time. Population 1 is like the sun, a live star. It's on the main sequence of the star. They're not evolved yet, right? Population 2 are all the evolved stars, like red giants and red supergiants. Whereas these guys are all population 2. These guys have population 1 and population 2. And that includes all of these guys. They have lots of dust and gas. So that's how they differ. That's where star formation is going on. And then you can see the tuning fork now, right? It's like goes like this and just tuning fork, right? That's what they call a tuning fork diagram. And then it closes at the end like this. And here we have I, R, R galaxies. IRR galaxies are irregular galaxies. Irregular because they're not like ellipticals, they're not like lenticulars, and they're not like spirals. If you can just have a spiral arm, that's what they're more like. So if you just take a chunk of the spiral arm here, that's what they look like, the irregulars. They have no nuclei, no nucleus at all. But all of these galaxies have a nucleus. Irregulars don't have any nucleus. So we say these have no nuclei. No nuclei. But they have everything else. They have population 1, population 2, lots of dust and gas. If there's any questions, please ask me. I'm just sitting doing nothing. Okay, can I go back? Are you guys all done?
You guys good?
You need a couple more minutes? Anybody needs a couple more minutes, say yes. All right, I don't hear anything. So I'll just change cameras. All right. Now let me show you guys what the heck is really going on. These are galaxies that are called, they used to call them very strange galaxies, but now they're kind of normal. These are collisions between two galaxies. And so take a look, we'll see what's going on here. You see these little red patches? That's called a starburst. That's where those red hydrogen clouds are glowing. This is where stars are being made in the spiral arms of the galaxies. So when they collide, all of a sudden there's a huge starburst. All of a sudden, star formation goes on rapidly. Milky Way is going to get into collision in about 4 billion years too. In fact, there is galaxies that are running into the Milky Way right now. There's one right there. But there's a tiny little galaxy, so we're just eating it up, basically. So here's another two galaxies that are colliding. So what happens when these galaxies collide? Weird things can happen. Like as an example, these two galaxies collided. The spiral arms changed shape and became like a ring galaxy. Very rare. You have to have like a bullseye collision to form a ring galaxy like that. Very strange. Most of the time you have this kind of a collision, where you take the spiral arm with you, like this. This is called a mice. So when these guys collided, the spiral arm moved out. And so when you take the spiral arm out, this chunk of the spiral arm can turn into an irregular galaxy with no nucleus. It's just a runaway spiral arm. And then the central portion can become an elliptical galaxy, because the center of the galaxies are population 2 anyways. Here's another collision. So they take each other's dust and gas, and what remains is the nucleus. And that's what elliptical galaxies look like. So elliptical galaxies are probably the evolution of spiral galaxies. When spiral galaxies collide, this is what happens. You end up like that. And so if you have smaller spiral galaxies colliding, you can get dwarf elliptical galaxies. You have the big ones, you get large elliptical galaxies. So Milky Way's probably had like 16 or 17 collisions. It's not like this one-time collision. We've had so many collisions. That's how galaxies grow in size, through collisions. At one time, the universe was so much smaller, so when the space was smaller, you had so many chances of collision. Like if you go to a party and there's 100 people in a small room, you're going to collide with somebody. You maybe spill their drinks or something. But if it's a huge gymnasium, there's 10 people in there, there's hardly any collisions. So as the universe gets bigger and bigger, chances of collisions are smaller and smaller and smaller. But at the beginning of the universe, there was a lot better chance of collisions. Does that make sense to you guys? Okay, that's how all the galaxies form, basically. All right. So you guys, I was going to show you guys how to use the image processing routines. I don't know if you guys can see this. Let me just go where I need to go, and then I'll show you guys. All right, so let me stop here, go back. Okay, can you guys see this now? It says astro imaging.
Yes.
Okay, thank you. So, okay, once your pictures come back now, right? This is how you open up the FITS images. I'm just going to show you guys a couple of videos, and then we're going to say goodbye. It's already 11:35.
In this tutorial, I'm going to show you how to open a FITS image using MicroObservatory. As a reminder, a FITS image that's FITS spelled F-I-T-S, is the most commonly used digital image type in astronomy. If you have already requested a FITS image through Microobservatory, you can find a link to it in your email. If you haven't, you might first want to watch the tutorial, How do I request an image? Okay, so first go into your email. You should see an email from Microobservatory support at cfa.harvard.edu with a link to the image you requested. If you requested an image yesterday and you still don't have an email, give it until the end of the day. Sometimes it takes up to 24 hours for the image to arrive in your inbox. Okay, so open the email, as I've done here, and click the link near the top that says access your image of whatever you requested an image of. If the filter you chose was more complicated, you might see a link that says access your ret filter, etc., or something along those lines. Or you might see several image thumbnails with several similar links for the red, the green, and the blue filters. But basically, however many images you were sent in your email, download them all, because you will need them all later. Since my email here only has one image thumbnail, I'm just going to download one FITS image now. So once you've clicked on the link and the image is opened in another web page, find the link on the page that ends in .fits, which is this link here. You should then right-click this link, choose Save Link As, and save this image somewhere you know you can find it. For me, I'm going to save it in a folder that I've called Microobservatory Images on my desktop. Also, as a note, this file has been given the name Saturn 170601083229, and that may seem like a crazy sequence of numbers, but it's actually the timestamp for when this photo was taken. So this 17 right here is for 2017, this 6 is for June, this 1 is for June 1st, and this right here is the time, which is 8:32 and 29 seconds. Okay, so I'm just going to save this in the folder. Now for an important warning. You've got to right-click and save this link and not the big image below it. This image is just a GIF preview to show you what the real image looks like, but it doesn't contain all the great information that comes with the FITS file. Next, go back into Microobservatory, which you can get to by typing microobservatory.org into the URL bar. Click on Observing with NASA, and then click on the Analyze Images tab up here in the bar on top. Analyze Images is where you will upload the images you just downloaded and do your image processing. Now you're on JS9, this whole box of space right here. JS9 is the application you use to process your new images, and is just like the software professional astronomers use to study their images. To open the image you just saved, the option you want is in the drop-down under Image. Click Open, and a dialog box will pop up. Figure out where you saved your image, which for me, if you remember, was in Microobservatory Images, and this is already the folder that's opening up automatically. Make sure you've got the right image type, which ends in .fits. If it ends in .gif, you probably downloaded the thumbnail image instead of the FITS image link a few steps back. Click Open, and there you go. You've got a nice new telescope image uploaded to JS9 and ready to be processed. And if you want to learn how to process this image, you should watch the How Do I Process a FITS Image tutorial too.
Okay. I think I should have stopped it, huh? Because it's probably going to keep playing. Yeah. All right, let me go to the next one. So Bethany, like you got your image, right? This is what you're going to do with your image once you get your image. Ay, 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 ay. Let me make sure you guys are watching the right thing. Okay. Can you guys see this?
Yep. Yeah.
Okay. Come on, man. Let's see.
Using red, green, and blue filter, a dark image to remove pixel noise. By now, you should have already learned how to create a standard RGB image in Microobservatory using red, green, and blue filters and RGB mode. If that doesn't sound familiar, you should probably go back and first watch the tutorial, how to create an RGB image. And then come back here, because we'll be building off of that tutorial in this one. Okay, let's start by going back to the email you got from Micro-Observatory Support with your red, green, and blue filtered images. These are all images of the Crab Nebula. But there's something else in this email that I didn't tell you about in the tutorial to create a simple RGB image. For an advanced RGB image, you'll need this fourth image here, which you'll see is called a dark calibration image. Let me first explain what the point of a dark calibration image is. When a telescope takes an image of an object in the sky, its light detector records the perceived brightness of each point in the sky onto each pixel in the image. However, the detector isn't perfect and includes little amounts of false brightness into some of the pixels in the image. We can refer to this false brightness as noise. So if we take a dark image, meaning when the telescope isn't exposed to any light at all, we'll know that any brightness that gets recorded is the noise that the telescope is adding to each pixel. And we'll then be able to subtract this noise out of our actual images. So back to this email. You should be familiar with this step. Let's download all 3 RGB filtered images, and this time the dark calibration image as well. I'll download the dark image first. Don't forget that what you want is this link here that ends in .fits. This image is just a GIF preview of what your FITS image looks like, but we need to work with the FITS file itself. I'll grab the red, green, and blue filtered images now too. The truth is that Micro-Observatory will send you a dark calibration image for any request that has an exposure time of 60 seconds. So you can do this advanced processing method with a lot of the galaxy and nebula images, not just the ones that offer RGB filters. And it's the same process as the one I'll show you here, it's just that you'd be using a dark calibration with 1 image instead of 3. But if you're just curious how to use a dark calibration image, you can also watch the tutorial, How to Use a Dark Calibration Image. So with our 4 FITS images saved, let's go back into Micro-Observatory at microobservatory.org. And as usual, let's go to the Observing with NASA portal. Since we already have the images we need, let's pull up the JS9 for Learners application by clicking on Analyze Images. Okay, so here we are in JS9, and let's bring in our 4 images. I'll do that by selecting all 4 images in this folder and dragging them into the JS9 window. You can see when I click on the My List dropdown that all 4 images have loaded into the application. Let's work with the top Crab Nebula image. Out of curiosity, I wonder what filter this image was taken with. Image dropdown, display FITS header, and it looks like this is our red filtered image. Now, normally at this point, we'd start changing scales and brightness limits, but for advanced processing, let's hold off on that for a second. The very first step here is to deal with the dark image and removing image noise. Okay, remember we have our red filtered image open? With that in mind, let's click on the Tools dropdown and choose Image Map. And here's the widget that allows us to remove dark image noise from our images. We might as well drag it over to the side where it won't be in the way. Because we're currently open on the red filter image, that's also the image that will be affected by this image arithmetic window. You can see the active file here is the same file name as our red image in My List. They both end in 082754. The first thing we have to decide is what to be done to our red image. Since we want to remove noise, let's select Sub for Subtract from the Operations dropdown. If we chose Add, we would be adding even more noise to the image, so we definitely don't want that. Next, we have to choose what we're removing. We're removing telescope noise, so choose Dark B in the Operand dropdown. One thing I should point out to you is that dark images are specific to the individual telescopes, not the objects they take images of. If you look at dark image file names, you'll see a letter after the word dark. These letters represent the first letter of the name of the telescope that took the dark image. B stands for Ben. And as you can see here, our blue filtered Crab Nebula was also taken with telescope Ben, so we've got the right dark image. Before we click Run, take a look at the pixel values of this image. When I wave my cursor around the dark areas of the image, the lowest pixel values I'm seeing are around 328 or 329. Okay, now click Run. You may notice that your image grew a little darker. And look, when I wave my cursor around the same dark area, the lowest pixel values are now around 8, 9, or 10. That's because the pixel value of each pixel in our dark image has been subtracted from each pixel in our red filtered image. This gives us an image without the telescope noise. Okay, now let's process this image as well as the other two after it. I'm not going to explain how all of these buttons and sliders here work, but if you're confused, I recommend you watch the tutorial How to Process a Fits Image. Okay, we still have the red image open in my list, meaning that it's in front for us to process. The first thing I need to do is enhance the image, and I do that by changing the scale to log and setting the low brightness limits to the lowest pixel value in the image, which is about 7 or 8 according to the pixel value here. I like the high brightness limit at about 1000. Next, we need to color the image based on what filter was used for this image. Go to the image dropdown and select Display Fits Header. Right, so here we are, filter equals red. So close this fits info, go up to the color dropdown, and choose red. There, our red filtered image now appears with the black and red color scale. Let's set red aside for the time being and choose the next image in our list. We're going to do the exact same thing as before, the only difference being which filter was used for this image. Now, don't forget that we're doing advanced RGB processing here. So the first thing we need to do is remove noise with our dark image. Now that we're in the second image in the list, when we look at the image math window, this file name now corresponds with the second file name in the list, meaning this is the image that will be affected. Same as before, you want to choose Sub, then select the dark image from the operand list and click Run. And with that, the dark image noise has been removed from our second image. Now to the rest of the steps. Change the scale to log, find the background sky pixel value, looks like it's about 5 or 6, update the low brightness limit, high brightness limit around, let's say 1000 again. Then figure out what filter this image was taken with. Looks like this image is green. Choose green from the color maps, and now our green filtered image has a black to green color scale. One left, so choose the third image in our list, which we can assume is the blue filtered image since we've already worked with the red and green images. Again, let's remove the dark image noise from this image. Go back to the image math window, which now lists the same file name as the third image in our list. Choose Subtract, select the dark image, and click Run. Now the third image has been updated, and we've successfully removed dark image noise from all 3 RGB images. So at this point, we can close the image arithmetic window because we won't need it anymore. One last time, let's change the scale to log. Find the minimum pixel value. Looks like it's 2 or 3, pretty low. Update the high brightness limit to, well,
1000.
let's just go with 1000 again.
Jesus.
We already have a good feeling this image used a blue filter, but let's just verify that. What do you know? Filter equals blue. Choose blue from the color dropdown, and now our blue filtered image has a black to blue color scale. At this point, we can close the dark image because we've successfully removed telescope noise from each of the 3 images. And with that, we're ready to combine our 3 colored images into one true color image. First, we need to be able to see all 3 layers at once. To do that, select RGB mode from the color dropdown. Now you can see the red, blue, and green image layers all on one screen. But they aren't lined up, so we have to shift them back into alignment. If you recall, the tool we need is in the Tools dropdown, and it's called Shift. I'm going to switch to the first image in my list as the layer to work with. And the color bar tells me that this is the red image. Sure enough, if I click around on these arrows, you can see the red image is shifting around a bit. This is a good layer to start with because it's easy to see. Now, I want to carefully line this up with one of the other layers. I'll use the green layer because it's also easy to see. I'm just clicking the layers into alignment. Remember that each click moves the layer 1 pixel in that direction. Don't forget that you can use the magnifier feature under Tools to make lining up layers much easier to see. And looks like red could maybe go up into the right 1 or 2 more times. Maybe back 1. And that looks pretty good to me. So let's line the blue layer up too, which was the third one. You can see the color bar down here is going black to blue. Okay, so shift that into place. Based on this spot, it looks like the blue image needs to go up and to the right a little bit, but not very far. The best way to be sure you get it just right is to observe the alignment around a bright star on a dark patch of sky, kind of like this one here. This is looking pretty good, so I think it'll do just fine. If you feel like anything is still a little off, you can switch between the layers for some last little tweaks. But I like the way it looks right now, so I'll save it as is.
That's it.
There. Not only do I have a fancy true color RGB image of the Crab Nebula, but I know that it's even sharper and more accurate than the version I created in the basic RGB tutorial, because I took the steps to remove pixel noise from each image layer first. And with that, you should now be able to create an advanced RGB image too.
Thank you. Sheesh. All right, well, that's how you do it, Bethany. Did you see? Yeah, we're not going to do a simple. We're actually going to remove the dark noise. What the dark noise is, it's actually the infrared from the heat of the camera registering with the detector. Because the detector doesn't just see light that we see with our eyes, it also sees infrared. So the electronics in the camera, they have heat, and so the camera picks up this heat, that's noise. So you remove the noise first, and then you have noise-free images, you put them together, move them around a little bit, done. Just exactly what he did.
Okay.
Okay, that's it.
Cool. Thank
So
you.
let's see how you guys can do. And then when you send it in, when you put it in Canvas, I can go in there and I can improve your stuff too. I can make it even better looking. So let's see how well you guys do. So make sure you guys put in for an RGB images, at least put 2 or 3, so that by Wednesday you guys have 2 or 3 images so you can do it. All right. Okay. Then Luke, why don't you give us a holler so we can get out of here? There you go. All right, thank you very much. Any other questions you guys have before we say goodbye and adios? So just one more lab, you guys. Remember, just one more lab we're going to do besides the Milky Way, and that's cosmology. We're going to do the universe, right? So I asked you guys something to get. Remember what I asked you guys to get?
A balloon?
Very good. Is that Bethany said that?
Nope.
Was that you, Talia?
Yep.
No, you guys are starting to sound the same, you know, it's kind of weird. All right, yeah, a balloon. So if you guys can get a balloon, now I have a few balloons. Normally I give everybody in the class a balloon. I just can't go to your house right now and give you a balloon. But get a balloon that, can go like about this big, It's a 12-inch balloon, it's not that big. I got this from Walmart. I was like, I don't know, the whole package was like a couple of bucks. So if you guys can get this by next week or something, it'd be pretty awesome. Can you guys remember that, or should I send you an email, remind you and everything? Because I know you guys are busy these days. So
I think I'll be able to remember.
you
I
will.
will.
All right.
I need an email.
Bravo, you guys gonna remember a balloon. All right.